Hello, my name is Matthew Nealon, and this is video 1 for homework 1. And in this problem, we are going to find how two radiuses with a given velocity profile and a given shear rate of a tank spinning around is that the torque on the inner and outer radius of the tanks are equal. So to start off, we will have our tank over here. Just a good example of what we're going to have. So a way of seeing that is just having this tank as such, and then it being able to spin around. Having it to spin around sort of in this space here. And another way to look at it is looking at the space from a top-down view of what's going to happen between the two. So we have two lines here. We have this line going here, this line going here. If you can see, is that this line from here is going to be the outer radius, so we're going to make that our capital R, and then this line here is going to be our inner radius, so it's going to be R. And what we know just based on our velocity or normal velocity profile is that our velocity profile of v theta is equal to the angular frequency times the radius. And because of the way this tank is set up, is that we know that the velocity profile at the outer radius is going to be 0. So how do we now try to figure out how both of these radii and how the torques at both of their points is equal? Well, that's how our shear rate comes in. So we're going to take this in cylindrical coordinates. So just a good way of separating these two systems off is that we're going to write just going to write our cylindrical coordinates and just to make sure we know what we're going to be working with. So what is our shear rate? Shear rate, that's not best. Set up here. So our shear rate is going to be equal to the radius. It's going to be equal to the radius times the derivative of the radius multiplied by our velocity profile divided by radius. This is our given shear rate. And how this relates to both of these questions is that our shear rate is going to be in tandem with something called viscosity. This viscosity kind of works like this. So at a particular point, we're going to have forces acting at different points in this fluid that's in between these two tanks. At the inner radius, it's going to have the largest amount of force because that's where it's rotating the most. But because of viscosity, we are going to have sort of not deteriorating, but the forces are going to get less and less until it reaches the outer radius where it's going to be 0. But that doesn't mean that there's no force acting on this outer radius, and I'm going to explain why with our velocity profile. So how do we go about trying to show that the torques at each end of this velocity each end of our radius are equal to each other? So with our given velocity profile, the theta is going to be equal to the angular frequency times k squared over 1 minus k squared. And k, just for your information, k is equal to the inner radius and the outer radius. That is the ratio between the inner radius and the outer radius. So from here, the rest of our velocity profile is going to be as such. It is going to be outer radius divided by our inner radius minus r minus the inner radius again. And just for clarification, I'm going to be switching between r and ri to just distinguish the inner radius. They are both exactly the same, but it is just a little easier to write r in this equation than keep writing ri over and over again to make a jumbled mess. So how do we do this? So how we're going to solve for the torque is that we're going to find an expression of our velocity profile that is equal to the shear rate, given all of our values here, and how we can manipulate this equation to get to our shear rate. So one thing we can immediately do right off the bat is take one of the inner radiuses and put it outside, so we can get our velocity profile divided by our radius of the inner. So our new expression is going to be a velocity profile divided by r is going to be equal to the angular frequency times our ratio k squared over 1 minus k squared. And then our new equation here is actually going to be r squared, or capital R squared, or our outer radius squared, over our inner radius squared minus 1. And now we can start using this take our derivatives. So we just need to take one derivative, which is the derivative of of all the radiuses, because this whole equation here is going to interact as a variable. So we're going to have our derivative of the radius over d theta r, and all of these are just going to act as constants for the time being. So we have our angular frequency, and then we have 1 minus our k squared. So we have our k squared minus 1 k squared. And then this new expression is going to be negative 2r squared, capital R squared, over our inner radius to a third. This is our new expression. And now, if you can tell, we can now take another r, or another inner radius, out of this and add it to our side just by multiplying each side by r. So now we have our shear rate expression, which is going to be r of the inner radius times our derivative of the radius multiplied by the shear rate over r equal to the angular frequency times k squared over 1 k squared, and it's going to be, actually we're going to rewrite this side to get it a little bit more clean. So when we start substituting, because at some point we're going to have to start substituting k into our either inner or outer radius portions here. So we're going to adjust this and say that, because we're going to pull this 2 out, so we're going to do this negative 2, and then our angular frequency times k squared minus 1 k squared, and then our new side here is just going to be r squared, our capital R squared, and r squared. So this is our expression that we're going to use to find how the torque is equal to each other. So this is our new shear rate. We're just going to draw a line here, and from here we can now start trying to find torque. And a good way to look at torque is trying to find how the two different styles of torque we can find. Torque can be found in 2 separate ways. So we're just going to write both expressions on each side here and then try to get them equal to each other. So our torque, we'll put the inner radius here and the outer radius here. So the inner radius, Ri, is equal to, and this is our new equation of torque that we're going to use, which is going to be our shear rate times viscosity. And our normal torque equation will be the force times the inner radius. So these two things are equal to each other. So how do we find force? In terms of this problem, our force is actually going to have a torque within itself. It's going to be the torque at the inner radius, and torque can then, force can be found by taking or finding the area of one of these circles, which is just going to be 2 pi r, not capital R, Ri, and then h. And this is going to be our area being found at this sort of shell. So this is going to be our area, and then we can substitute this force back into this equation. So we're going to have a new torque problem here, or a new torque equation that's going to be torque times 2 pi Ri squared times h. Because we have to plug this Ri in as well. And now we want to take this torque equation and plug it in to this torque equation. So we don't have an equation for viscosity, and we're not going to. However, we do have an equation for our shear rate, and we're going to plug that in as such. So our new torque equation is going to be as such. It is going to be our viscosity times our angular frequency times I'm missing some stuff here. Times our angular frequency. And we don't need the negative because this is all in cylindrical coordinates. It's not going to matter which way it's going to turn. Because if it's turning negative, then it's not going to affect the forces. So we're just going to take the negative out because it makes this process a lot less messy. So we have 2 times the angular frequency times k squared over 1k squared, and then we have our other side here, which can be capital R squared and then R squared. So how does this differ depending on the shear rate? And that is where our K value comes in. Because if we want to find the shear rate at the inner radius, we need to take our K value at the inner radius, or solve our K value for the inner radius. So what we're going to do now, just to state up here, so we can say that our Ri value is equal to K R. Our Ri value is equal to K capital R. So that is an expression we can substitute here into our normal inner radius value. And we're just going to rewrite the equation right now, just conserve a little bit of space. We're going to rewrite this equation as such. Due to this, our K value, our K squared value, and our capital R value are both going to get eliminated from this equation due to Ri being squared and canceling out both terms. So we now have a new equation as such. This is what we're left with. And now we can plug in the rest of our equation, which is going to be the 2 pi r squared times h. So now we have our 2 pi ri squared times h. So this is our torque at the inner radius. So what if we come over here and do the exact same thing, except we were to solve the torque for our outer radius? So we're going to erase that line because we're going to eventually draw all the way down to here. So we're just going to rewrite what we had over here, except in terms of our outer radius. So we have our torque of the outer radius is equal to viscosity times shear rate. Actually, I'm going to rewrite that one bit. I notice on the camera that's a little small. So this is our new expression, and then we are going to take torque at our force times capital R. Then we can say the exact same thing. So our force is going to be equal to torque at 2 pi r times h, and then our torque of r is going to be equal to torque of r again at 2 pi r squared h. And then we're going to substitute this back in, but we're going to then take our r value in terms of our, k value, in terms of our r value. So we're going to be left with a new expression as such. So our torque of the outer radius is going to be so we're going to substitute this back in, so it's going to be our viscosity times 2 times the angular frequency minus k squared. And then it's going to be, and due to our ratio, we are going to actually keep our k squared value because the r squared and the ri squared will actually cancel each other out, at least in this form, on this side of the equation. And then we're going to be left with 2 pi r squared h. Write that, r squared h. So these are our torques at the inner and outer radius. So how are we going to prove that they're equal to each other? Well, we set them equal to each other and see what cancels out of the equation. So let's just go down the line. So we both have viscosity in our equation, so we're going to cancel that out and cancel that out. Also, if you notice, we have a 2 and a angular frequency on our sort of left-hand portion of it. So we're going to cancel both out. And then we can go to our area and see what is common. We can see that our 2, our pi, and our height are all equal terms that we can then cancel out. So we're going to say 2 pi h, 2 pi h. So what are we left with now? We're now left with a new equation as such. It's going to be ri over 1 minus k squared. Let me write that a tiny bit bigger. We have that ri squared over 1 k squared is equal to our k squared r squared 1 minus k squared. So if you notice that we have a good thing going on here where our denominators are exactly the same to each other. But however, if you notice is that our Ri values, our Ri is actually equal to the other side, where Ri is equal to K times R. And since both of these are squared, all these are squared to each other, they all cancel out. Both of these cancel out. So at the end of the day, what does this mean? Well, this means that if this tank here is spinning and this one is stationary, that means that there's a torque operating or getting that's pushing on this tank. But if the tank is stationary, how come there's a force on it? But if the tank's stationary, it means that it's resisting the torque. And a good way of seeing that is that we have our first tank here, and it's going to be spinning this way. And we have another tank just around it with some fluid in between both of these tanks. And our tank is going to have to technically spin that way to resist the motion that this tank does. And because of our viscosity and our viscosity, our shear rate, and our velocity profile, these forces are going to cancel each other out.